Hello students, welcome to the session. So I am Santosh Gondi. So in this session we are going to see electronic devices questions which have been asked in GATE 2020 Electronics and Communications. So now I wanted to thank my team for bringing these questions. We have received only 3 questions where we are having a clarification regarding the question. So if you are having more questions, you can definitely post to us in the comment section. So first of all, let us go into the very first question that we have received. This is a 2-mark question that has been come in the examination. This is on the topic of solar cell. Okay, this is on the topic of solar cell PN junction theory. So first of all, let me read the question. A PN junction solar cell of area 1 centimeter square. So the area of the solar cell is given as 1 centimeter square, uniformly illuminated with 100 milliwatt per centimeter square, has following parameters. So what is given here? A solar cell. It is given that we are having a solar cell. The area of the solar cell is 1 centimeter square, and the optical power, which is power density, which is incident here, is 100 milliwatt per centimeter square. And the following parameters are also mentioned in the question. Number 1, the efficiency of the solar cell is given as 15%. VOC, the open circuit voltage, is given as 0.7 volts. Fill factor is given as 0.8. Thickness is equal to 200 micrometers. See, I think in the classroom also we have discussed that this topic is a very important topic in the examination point of view. Consistently, the questions have come in 2017, 18, 19 based on this particular topic. So there is no surprises that the question has come from solar cell in this. So 2021 aspirants who are preparing, please take this topic very seriously. You should have a clarity regarding this concept if at all you are expecting very good marks in the GATE examination. So let us try to solve this problem. The question here that is asked here is the average optical generation rate. The question is about the average optical generation rate. So the unit of the generation rate which is given in the question is per centimeter cube second. Is dash. What are the options given in the question? The options given are 1.04 into 10 power 19. Option B 5.57 into 10 power 19. Option C is 0.84 into 10 power 19. And the last option is option D, 83.6 into 10 power 19. So these are the 4 options which are given to us. Okay. So we have to solve the problem. So how are we going to solve the problem? Using the help of the efficiency. Efficiency is nothing but what? It is nothing but the maximum electrical output power divided by the input optical power. So we know here the area of cross section is 1 centimeter square and optical power is 100 milliwatt per centimeter square. It means that the total optical power that we are having is 100 milliwatt per centimeter square. So optical power is 100 into 10 power minus 3. Maximum power which is generated, electrical power we are talking about, this is given by fill factor multiplied by ISC multiplied by VOC. This is the formula. Efficiency is given to us, yes or no? Efficiency is given as 15%. So I would consider this is 0.15. This is equal to fill factor. What is fill factor? 0.8. 0.7 is the value of the VOC. ISC, something which is unknown here, divided by, I can consider this as 0.1. So I can find out the value of ISC, which is 0.15 into 0.1 divided by 0.56. So we can calculate this value. I think this value will come to 26.78 milliampere. This is the value of ISC that we are going to get. Right. So now what I would do is that this is a solar cell on which we are incidenting the optical power, right? We are incidenting the optical power. The meaning of short circuit current is that when you have short circuited this solar cell, when we short circuit the solar cell, the current which is flowing through it is what we are calling it as ISC. So current, as we all know, the current is given by the charge flow per unit time. So time is not mentioned, so we will consider it as 1 second. Per unit time is per second. So charge per second which is flowing is Q per second. The amount of charge which is flowing through this is Q per second. So how can I write this Q? let me write this Q as N multiplied by Q per second, where N is the total number of charges per second, right? So ISC is 26.78 into 10 power minus 3. If I divide it by Q, the amount of charges per second I'm going to get is equal to what? 26.78 into 10 power minus 3 divided by the charge of the electron, which is 1.6 into 10 power minus 19. This value, if you're solving this, you're going to get the value of this as 1.62 into 10 power 17 charge, number of charges per second. This is the number of charges which is flowing per second. Now we wanted per centimeter cube second, right? It means that whatever you got, we are going to divide by volume, so that you're going to get in terms of per centimeter cube second. Okay, so here we have to note that whatever number of charges are there, these are number of charges per second, but we wanted in the question it is given, it should be per centimeter cube second. Okay, so if I divide by volume, what is the volume? Volume is given, I mean whatever charges you are having, 1.62 into 10 power 17 divided by the volume. Volume is given by area. Area is 1 centimeter square, multiplied the thickness. Thickness in the question is mentioned as 200. So 200, please remember, students do a mistake here, and that is the reason why option is there here. Say 200 into 10 power minus 4, because we have a habit of always writing micro as 10 power minus 6. We will do a mistake. We should ensure that it is there in centimeter. So in terms of centimeter, 1 micrometer is equal to 10 power minus 4 centimeters. So let me substitute that. So 200 into 10 power minus 4. So this value, so you can cancel out zeros, 10 power 15 here, so it becomes 10 power 19 over here. So 1.62 divided by 2, it becomes 0.81. 0.81 into 10 power 19 is what we are having per centimeter cube second. Per centimeter cube per second. So 0.81, in the options it is given 0.84, so it is very close here. 0.84 into 10 power 19 per centimeter cube per second. So the answer for this question is option C. The answer for this question is option C. Option C is the correct answer for this question. Okay, so till here it is very much what we have discussed in the class. So this is the step that we have to be careful about, because this is a new thing that has been added in this year. Okay, so the answer for this question is option C. Now let us move on to the next question. And the next question that we are going to discuss is from the topic of Fermi level. I'm telling you once again, solar cell is a very, very important topic. So the future aspirants, GATE 21 aspirants, we have to take this topic in electronic devices very seriously. Electronic devices, this year, the paper is on the difficult side. And this is very obvious that not all the papers are going to be easy. So here, the electronic devices standard of the questions are on the difficult side, which will generally happen that some subjects will be easy, some subjects will be difficult. So this is the turn of electronic devices to be difficult. So it will be a learning for you that whatever subjects you are targeting, you should ensure that we are learning it to the best possible extent, and going to the examination, the practice is key for any subject to do well in the examination. So students who have missed out the yesterday's analysis video, I would request all of you, after completing the question solving session today, you please go through the analysis video which we have made yesterday, which will throw little insights on how the paper is. And if you are a future aspirant, GATE 21 aspirant or GATE 22 aspirant, then we have given insights of how you have to prepare, how you have to pace your preparation. Right, so now let us move on to the next question. So the next question that we are going to discuss here is a 1 mark question. Okay, it's a 1 mark question that has been asked from Fermi level. So first of all, let me read the question. So this is from the chapter of semiconductor theory. A single crystal intrinsic semiconductor at T is equal to 300 Kelvin. So the temperature of a semiconductor is given as 300 Kelvin. The effective density of states for holes. This is a very, very important sentence. Please be careful. The effective density of states for holes is twice the effective density of electrons. The effective density of states for holes is twice the effective density of states for electrons. So a very important statement which is given to us. And it is also given kT, the thermal energy, is equal to 26 milli electron volts. 26 milli electron volts. Now the question is that the intrinsic Fermi level is shifted from the mid band gap energy by dash. Mid band gap energy by dash. Option A is given as 26.9 milli electron volt. 26.9 milli electron volts. Option B is 9.01 milli electron volts. Option C is given as 13.45 milli electron volts, and option D is 18.02 milli electron volts. Right, so these are the options which are given in the question. So we have to find out the Fermi level shift from the mid band energy level. In the classroom we have learned that the intrinsic Fermi level for an intrinsic semiconductor is given by EC plus EV. So what is EC? EC is nothing but the minimum energy level of the conduction band. EV is the maximum energy level of the valence band divided by 2. So this is what is referred as the mid band gap. This is what we are referring as the mid band gap minus kT by 2 ln of Nc by Nv. So the intrinsic Fermi level is given by EC plus EV by 2 minus kT by 2 ln of Nc by Nv. So what I can do here is EI minus EC plus EV divided by 2. So because the question is all about the shift of the Fermi energy level from the mid of the band gap, so this is the shift value which is equal to minus kT by 2 ln of Nc by Nv. Ln of Nc by Nv. What is kT given as? KT is given as 26. So divided by 2 is 13 milli electron volts. 13 into 10 power minus 6. I'm sorry, 10 power minus 3 ln of Nc by Nv. So minus 1 by 2, because Nv is equal to 2 times that of Nc. Nc gets cancelled out. So I can write it as 13 ln of 2 milli. The unit is electron volt. Milli electron volt. So 13 ln of 2 will come to option B. So option B is the correct answer. 9.01. If you solve this value, please understand this is ln. Okay, it is not log, it is ln, natural logarithm. So it is going to be 9.01 milli electron volts. 9.01 milli electron volts is the correct answer. So option B is the correct answer for this question. Option B is the correct answer for this question. So if you have learned the Fermi energy level, then definitely you can be in a position to answer it, because this is one of the famous formulas that we have in the concept of Fermi energy level. Fermi energy level. So now let us move on to the next question. If you're having any doubts in this question, please ask. Meanwhile, we will move on to the next question. So Fermi energy level theoretically is an important concept. Not many times the question have come from this Fermi energy level topic. But yes, we cannot ignore this topic. Okay, even in the classroom we have discussed that we cannot ignore this topic. This is one of the very important topic in terms of understanding, because of the fact that every chapter we will be discussing about Fermi energy level. Okay, whether it is a semiconductor theory, graded semiconductors, or when we move on to the Fermi energy, PN junction concept, or we move on to the BJT concept, or we move on to the MOSFET concept. So every time we discuss about the Fermi energy level, what is Fermi energy level? It is the maximum energy level that an electron can possess at T is equal to 0 Kelvin. Or after the concept of Fermi Dirac function, we can also represent Fermi energy level as the energy level which is having a probability of 50% occupancy of an electron. So the probability that an electron can occupy an energy level with 50% is what we are calling as a Fermi energy level. It's an important topic in the examination point of view. It is also important now in the understanding point of view. Understanding comes first, examination preparation comes next. So understanding has to be very clear, for which Fermi energy is one of the very, very important topics. Now let us move on to the next question. So this question is from one of the favorite areas of the GATE exam, which is MOS capacitor. Right, so it belongs to the chapter of MOSFET. So first of all, let me read the question. So if you ask me about the difficulty level of this question, I would say it's moderate level. It's not very difficult. It has been asked for 2 marks. Okay, first of all, let me read the question. A MOS capacitor is made of a semiconductor material of band gap 1 electron volt. So it is given that this MOS capacitor is made of a semiconductor which is having a band gap of 1 electron volt. The energy band diagram of MOS capacitor is as shown in the figure below. So let us see the figure. So here is the vacuum energy level. So you can see the separation here as 4 electron volt from the conduction band. This is for the semiconductor which is given. And you're having the mid energy level, Fermi energy, intrinsic Fermi energy level EI. And you also have the Fermi energy level for this material. Can you please tell me which type of semiconductor it is from its Fermi energy level? Is it a P-type semiconductor or an N-type semiconductor? So this is the Fermi energy level which is given to us. Can you please tell me which type of semiconductor it is? Is it N-type semiconductor or P-type semiconductor? So this distance, obviously it is given as 0.5 electron volts. And here it is given as 0.2 electron volts, this part. So totally it is given that it's 1 electron volt. In the question itself it is mentioned that it's a 1 electron volt. So mid is 0.5. So this should also be 0.5. This is given as 0.2. It means that this part has to be 0.3. What is this point? This distance is nothing but the Fermi shift. This is what we call as the Fermi shift. So Fermi shift is given as 0.3 electron volts. 0.3 electron volts. Okay. So this is the data which is given in the question. The energy band diagram is given for us. The energy band diagram of the MOS capacitor is shown in the figure below. So this is for the semiconductor part. COX is equal to oxide capacitance. COX is given by 100 nanofarad per centimeter square. So COX is equal to 100 nanofarad per centimeter square. So this data is given. Very important detail is given in the question, which is threshold voltage, which is minus 0.16 electron volts. And the metal work function is given in the question to be 3.87 electron volts. This is a metal work function which is given in the question. Now what is asked here is the magnitude of the depletion charges per unit area. Magnitude of the depletion charges, magnitude of depletion charges per unit area. Magnitude of the depletion charges per unit area is what is the question over here. So what we can do here, we can write here the threshold voltage. We know the threshold voltage, right? The threshold voltage is given by 2 phi f, which is the surface potential, 2 phi f, which is the surface potential, plus minus q divided by COX, which is the voltage across the oxide layer, plus the flat band voltage. What is the flat band voltage? Can you please tell me? Yes, very good, Rahul. Yes, it is a P-type material. Yes, very good. Good. So what is the meaning of flat band voltage? Flat band voltage is the voltage that we are applying through the gate terminal so that our energy levels are going to become flat. So that our energy levels are going to become flat is what we are calling as a flat band voltage. Generally, we have to apply this voltage because by nature, you are not going to have a flat band, you are going to have a band bending. So to remove this band bending, we are going to apply an extra voltage which we are calling as a flat band voltage. Now there are two very important reasons why we are applying the flat band voltage or why the band bending is happening. Number one is because of the metal semiconductor work function difference. So we call it as a Q phi ms. Metal semiconductor work function difference. This is the reason, one of the reason why we are going to have a band bending. The second is because of the fixed charges which are present inside the oxide layer. In this question, there is nothing given in the question as of now. What we can see over here, nothing is mentioned regarding the fixed charges. So we can assume that there is no charges which are present, which is trapped inside. So only reason why we can have the flat band voltage is because of the work function difference. So phi m is already mentioned in the question. I think we can easily find out the phi s. What is phi s? Is a semiconductor work function. The semiconductor work function can be given by vacuum energy level minus the Fermi energy level. Vacuum energy level minus the Fermi energy level. So you're having 4 here, here you're having 0.5, here you're having 0.3. It means that totally from here to here, the distance between the vacuum energy level or the energy gap between the vacuum energy level and the Fermi energy level is nothing but the work function of the semiconductor. So totally you can have 4 plus 5, 0.5, 4.5 plus 0.3, it is 4.8. So totally you're having 4.8 as the work function over here, 4.8. So phi ms, q phi ms is going to be equal to the top 4.8 minus, I'm sorry, phi m minus, so q times it off, phi m minus phi s. Okay, here also I'll mention q because we are having in terms of electron volts. Okay, so here also q is the result. So q phi m is going to be 3.87 electron volts minus q phi s, which is 4.8 electron volts. So if you do the subtraction, what is this value? It is minus 0.93 electron volts. It is minus 0.93 electron volts. This is nothing but q phi ms value. Okay, so this value we are having. Now this is going to be the flat band voltage for us. Okay, so flat band voltage is nothing but q phi ms value, which is minus 0.93 electron volts. So 2 phi f, we know phi f is going to be 0.3. It means the 2 phi f will be 0.6. So here COX is given, we have to find the charge over here. So VTH is a threshold voltage which is minus 0.16. I'm sorry, it is not in terms of electron volts, it is volts, okay? Because it's a threshold voltage, it will be in terms of volts, it's a voltage. So minus 0.6 volts is equal to the top 2 phi f. What is 2 phi f? 2 phi f is 0.6 as we have discussed. Minus Q divided by COX, we can take it as 100 into 10 power minus 9 plus VFB. What is flat band voltage here? Flat band voltage here is nothing but work function difference minus 0.93. Minus 0.93. So basically, if you want phi ms, what you can do is that phi ms is equal to 1 by Q times the top minus 0.93 electron volts. This will give you in terms of voltage, which is going to be minus 0.93 volts. So from here, you can find out, you can take the to the other side, 0.93 minus 0.16 minus 0.6 is equal to minus Q divided by 10 power minus 7. So I think you can calculate this value. It is this comes to 0.17, right? This comes to, so you're having 0.76 here minus 0.76 here, 0.93. Its value is 0.17 is equal to minus Q divided by 10 power minus 7. So Q, which is going to be equal to minus of 1.7 into 10 power minus 8. 1.7 into 10 power minus 8. So options are given as 0.52 into 10 power minus 8. Option B is given as 0.93 into 10 power minus 8. Option C is given as 1.7 into 10 power minus 8. And option D is given as 1.41 into 10 power minus 8. So the answer has to be 1.7 into 10 power minus 8. 1.7 into 10 power minus 8 should be the correct answer, because the magnitude is asked. We should not we should ignore the sign of it because of the fact that the magnitude has been asked in the question. So it is 1.7 into 10 power minus 8 coulomb per centimeter square is the answer for this question. Okay, so option C is the correct answer. I'll repeat the options once again. 0.52 into 10 power minus 8. Option B is 0.93 into 10 power minus 8. Option C is 1.7 into 10 power minus 8. And option D is 1.41 into 10 power minus 8. Option C is the correct answer for this question. Okay, so whatever questions we got the clarification based on the questions that have been asked. So basically these are all memory based questions that we have received. So wherever we have received clarification, we have made a video on it. So we know that there are further more questions in electronic devices. Once we get the entire details of the questions, we will definitely record those questions as well. So if you like this video, please share with your friends, okay, and also subscribe to this channel to get more instant notifications regarding any updates we are going to put for the GATE examination. And for GATE 21 aspirants, I would definitely suggest you to go through the analysis video that we made yesterday, which will help you to if it will definitely help you to actually start your preparation, when to start your preparation, what are the cares you have to take. We have put light on that in the analysis video. GATE 2020 students whose examination is not up to the mark, or you're feeling disappointed, then also I would suggest you to go through the video, because we have given details of what we have to do if if our gate performance is not so great. And the analysis video will give you an overview of how the paper is. We have seen that there are quite a few channels which have given the updates regarding it. So we have made a very detailed analysis based on the paper, after talking to all the subject matter experts that we have in our system. So based on that, we have made an analysis video. I'm sure this will be helpful for you. So with these words, I wanted to say thank you, and thanks for all the love and support that you are showering on us from your side. Thanks a lot, and wish you all the very best.